Around the world, electric vehicle production and adoption is ramping up. And one of the first questions any potential driver has is how charging of these vehicles works. This video runs through the basics of electric vehicle charging, including connector types, AC and DC charging, and some basics about back-office platforms. The first thing to realize is that the basic concepts are not complicated. Quite simply, electric vehicles use batteries as their power source, and like any other rechargeable battery that you may be familiar with, this requires a charger to replenish it when it is depleted. Batteries require DC power to charge them, while the power that comes from the grid supply is AC. The charger will therefore need to convert the AC to DC. The charge cycle also needs to be carefully managed according to what the battery requires at any point in time, so a charger must also supervise the recharging process. All electrical vehicles have a charger built into them so that they can take an AC supply from the grid and convert it to the DC power that their lithium-ion batteries require. However, this kind of charger is typically limited in capacity, for example 7 kilowatts, because it needs to be small, lightweight, and cost-effective enough to be built into the vehicle. This also means that it will charge the vehicle relatively slowly, and depending on the AC supply available where you are charging, you may even charge more slowly than the charger's actual capacity. To ensure that the vehicle's internal charger can operate at full capacity, an AC charging station permanently connected to a dedicated supply, for example in your garage or at the office, enables you to charge the battery faster. Even with your internal charger running at full capacity, it is still not fast enough for some use cases. A much faster way of charging EV batteries is to supply them directly with a high-power external DC charge. A large supercharger, for example, with a 100 kilowatt capacity, is able to bypass the internal AC-powered charger in the vehicle and supply the batteries directly with this DC current. This is the essential difference between AC and DC charging. The reason that we don't always use DC chargers is that they are far bigger and more expensive units than AC charge points, and so only make sense in certain use cases like public charging stations on the freeway or charging fleet vehicles where a fast recharge turnaround time is required. Looking more closely into the differences between the types of charging, we find that there are three commonly referred to types or levels. Level 1 is AC charging at 120 volts, which has a capacity of about 1.3 to 2.4 kilowatts. Given the very low power transfer and regional nature of that standard, it is not common. Level 2 usually also refers to AC charging, but at the more common 230 volt or 400 volt standard used elsewhere. They can be either 1 or 3-phase, and the higher voltage gives a power range of between 2 and 22 kilowatts. What has sometimes been informally referred to as Level 3 charging is more accurately referred to as HPDC or High Power DC charging. Also called DCFC for DC fast charging, this type of charger has a theoretical maximum power of around 500 kilowatts with current standards, but is more typically between 25 and 270 kilowatts depending on various factors, including the ability of the vehicles themselves to receive the charge. To give an idea of how these different standards translate into a real-world scenario, this chart shows the typical power of single-phase AC, 3-phase AC, and DC chargers. Note how the increase in power for each of these affects the time required to charge a typical vehicle enough to travel 100 kilometers. Note that while these figures help to understand the concept, it's important to know that they will change according to variables like battery temperature and state of charge. Most vehicles will charge faster for the first 80% or so of the battery's capacity, but will charge the last 20% at a much slower rate. That means that the time to charge 100 kilometers of equivalent energy will somewhat depend on the battery's state of charge during the charging session. So, will every EV owner be able to charge their car at these levels? The answer depends on the specific vehicle. Each vehicle is delivered with a particular capacity AC charger built in and also has a limit on the DC power input it is able to take directly from an external charger. This graphic shows a selection of popular electric vehicles with their maximum AC and DC charging capacities. These are important figures because using either an AC or DC charger with a higher capacity than these specs will not charge the batteries any faster. As the EV market has expanded, so too has the range of connector types used. While this may seem confusing at first, it is relatively simple in the South African market. This graphic shows the connector types used in different parts of the world for AC charging and for DC charging. South Africa has adopted the EU standard, which is a Type 2 charger for AC and CCS2 for DC charging, so most vehicles will conform to this. The chargers operate either as open points for anyone to use or as closed devices which require user authentication before charging can begin. Open points allow any user to plug their EV in and they will commence charging, as might be found in a private home. Closed points will require an RFID card to activate the charger and allow it to be used. This will often have a back-end software system managing it. This may be used in the examples of a public charger that requires payment for use, or a hotel that only allows guests to use the charger, and so on. The back-end system is an essential component of any charger network. It allows for functions such as determining if a charge point is active and online, rebooting charge points, starting and stopping charging sessions remotely, unlocking the connector from the vehicle remotely, analyzing charge sessions, managing authorization tags, billing customers for their charge sessions, and supporting the network. EV Backoffice is Rubicon's charger back-end system. It adheres to the OCPP protocol, which allows EV Backoffice to communicate with OCPP-compliant chargers. Another important point to consider is network roaming and interoperability. Networks running a backend which have roaming agreements in place effectively expand the network of chargers that a customer will be able to use. EV Backoffice's dashboard allows for monitoring of charging sessions, transactions, maintenance of charging points, and all the other functions required to manage a charger network. Rubicon offers a range of chargers from private to network level from the world's industry-leading brands in both AC and DC varieties. Contact us to find out how Rubicon can help you to pave the way to an EV future.